All right, so we're going. We're good. Okay, so what we want to talk about for the next couple of days is how we represent concentrations of solutions. All right. So when we dissolve a substance, we have a certain amount of the solute, the thing that we're dissolving, and we put it into a liquid, predominantly a liquid. If you did the reading on the textbook, you've also learned that we can have solutions that are of different states of matter, right? So you can have air, like itself is a solution. It's a mixture of molecules, and we can add molecules to it. You can have solid solutions. They tend to be what we call alloys. They tend to be metals dissolved in other metals. But typically, it's a substance dissolved in a liquid. So when we talk about concentration or how concentrated it is, it's usually represented as a ratio of some sort of the solute, the stuff that's being dissolved, divided by the amount of solution. Now, this equation right here, you will never use, right? So don't use, right? Don't use. Because we're going to be teaching you specific versions of the concentration equation. Today's lesson is on percentage concentration. It's a type of calculation we do to find what percentage of the solution is the solute. And tomorrow we're going to learn about molar concentration, and it talks about how many moles of the solute are dissolved in the solution. So we have different ways to represent the quantity of solute over the quantity of solution, but in general, any concentration calculation will have the stuff we're dissolving on the top and the solution on the bottom. So that's what this represents. Now, just qualitatively, a couple of terms that, whoops, too far. Qualitatively, a couple of terms that we use when describing solutions. We can describe a solution as being dilute, or we can have a solution being concentrated. And again, these are very qualitative terms. We have no official, official number that represents something that is dilute. But if you've ever made, let's say you made some juice, whether it's Kool-Aid, back in the day we drank tons of Kool-Aid. Kool-Aid seems to be not so cool anymore. Or if you're making some kind of beverage from a concentrated, like concentrate is the term they use, like say lemonade or orange juice. And I'm sure you're very aware that if you put way too much water into it, you get a watery version of the beverage. And some people dislike that. I'm a fan of the slightly dilute juice making. And so you already have experience with these terms. You may not have ever used them, but if they put lots of water in it, right, so you've got a small amount of the concentrate with lots of water, then you've created a dilute juice solution. And if you use less water, it's really sweet, and again, my personal preference is that it's disgustingly sweet, and then you have a concentrated juice solution, all right? So again, terms that you've probably had experience with, and these are terms you've probably heard of before. These are not like crazy out of the world scientific terms. Dilute means that it's weak, right? And concentrated means that it's strong. There's a lot of that stuff dissolved. Okay, so there's some general statements about solutions. Now let's talk about percentage concentrations, and I'm bringing up the whole thing because I rearranged the note from what it was in the past. And like I said, I've changed the way that I want to do calculations with this. I've changed it quite drastically. If you're looking at the note online, I may not have actually made a link to this new note, so you might be looking at an old note. So you might have to just kind of hold off on the PowerPoint because I may not have linked this to the website yet. Actually, I know I didn't. I forgot to do that. So we're going to be doing percentage concentrations. There are many different percentage concentrations, and you've experienced them before. I'm sure you've seen them. I guess one that you would have seen quite commonly is on milk, right? You get a glass of milk. If your parents buy 2% milk, right? And you see that on there, it's 2%. What is it 2% of? If you look a little closer, it's 2% milk fat. That's how much of the fat portion of the milk that they've left with the milk. If you have, ever gotten a cut or something and your parents like to use hydrogen peroxide to clean the cut, if you've looked closely at the hydrogen peroxide, you may have noticed that it says 3% hydrogen peroxide, all right? 3% of that volume is the hydrogen peroxide molecule. Now, of course, you guys aren't old enough, of course, but, if you've ever looked at a bottle of beer, right, and you'll notice in the corner it says 5%, right? And again, that's 5% ethyl alcohol or ethanol in that particular container. 5% of that container is the active ingredient, in this case, ethanol, right? If you're talking about, whiskey or vodka, 40%, right? So that's a concentrated version. And if you look closely on labels, you'll see it all over the place. Toothpaste, you'll see down at the bottom the active ingredient. If it's got fluoride in it, it might be sodium fluoride. It'll have a tiny little percentage in there, okay? So we're talking about percentages. So if I want to calculate the percent, just like we calculate any percentage, what I'm interested in, the stuff that was dissolved, divided by the total, just like you do a test, the total, times 100 gets you the percent concentration. Now, sometimes we want to find the solute or the solution. And so in that case, if we're calculating, how much solute is in there or how much solution I can make, I suggest highly that we write it down as a ratio. So when you have a percentage concentration, if you have something, for example, like 5%, that percent, remember, means per 100. So you can easily write that as 5 per 100. And when we do the calculations to find, say, the solute or the solution, I suggest we write it as a ratio, because really it's just a ratio. What percent means is, if I had 100 milliliters of solution, then I would have 5 milliliters of the solute. So I can put together that ratio. 5 per 100 is equal to the ratio of the solute and the solution. And so that's the way I'm going to teach it this time instead of using conversion factors. Concentration is a simple ratio where the percentage is always out of 100, and then we can calculate the amount for whatever solution we're actually using. Okay, now there are 3 different versions of the percentage calculation. There are 3 different ways in which we can deal with it. And the first one is called percentage volume by volume. So now what I'm doing is I'm adding to the equation I gave you last time. We're now putting units with it. Volume by volume is typically when a liquid is dissolved in another liquid. So we will be using volume units in this version of the equation. An example of volume by volume, I'm going to put down here, I'll use a different version. We'll use 13%, and this is ethanol in, let's say, a bottle of wine. All right, it's about 13% usually for wine. Again, ethanol is a liquid, and it's dissolved in water. So we could generate our ratio. It means that if I had 100 milliliters of wine, there would be 13 milliliters of ethanol. So from the 13%, we can say 13 milliliters ethanol per 100 milliliters of the solution, in this case, wine. All right? Now, when we do calculations, we're not going to necessarily write out ethanol and wine, so we could write that as 13 milliliters per 100 milliliters. Okay? Percent per 100. Now, depending on what question I'm asking, I will then have another ratio on the other side, and we'll then solve for the unknown. Okay? All right. So volume over volume, when we see V over V, what we're thinking is milliliters, a volume unit, over milliliters, a volume unit. Okay? Volume over volume. It's telling us the units that we're measuring in. Another version of the percentage calculation, again, I'm not sure where everyone's at, because this isn't online, so you're all following me here today. So if we, we're looking good here. The other version, the second version, is weight by volume. Sorry, we'll bring it back. Weight by volume. Typically when a solid is dissolved in a liquid. Now, we weigh grams on our scales. So in this case, we'll be talking about grams per milliliter. I could pick many examples of weight by volume that we use in the chemistry lab. Many of our solutes are solids. So I could make a sodium hydroxide solution, and I could weigh that sodium hydroxide solution and put it in so many milliliters of water. That would be a weight by volume of sodium hydroxide. An example that uses weight by volume, and I've already mentioned it, an example that uses weight by volume is, again, the milk industry. And the question is milk fat a solid or a liquid? It doesn't matter. They're weighing it. So if we had 3%, I don't know why I picked 3% milk fat, right, in milk, that's typically represented as a weight by volume. And that would mean 3 grams of milk fat would be found per 100 milliliters of milk. Okay? Again, percent per 100. And when we start doing questions, that will be equal to the ratio of the solution we're actually studying, and we will put the other ratio in the other side and we'll solve. But the key to weight per volume or weight by volume is it tells us that we have grams on the top, that's the weight, and we have milliliters on the bottom. So when we see weight per volume, that's the ratio we use. Okay? All right? Somebody's watching something exciting up there, I think. I don't know what it is, but it's very musical. Yeah. Okay, so one more version. And I don't know if we're seeing the trend, but the last version is W/W. Weight per weight, or weight by weight. And, oh, notice I have there, it says solid dissolved in a liquid. That's typo. I cut and pasted these slides, and there's a typo there. Solid. It is used for solids dissolved in other solids. Now, to dissolve a solid in a solid, that's a tricky maneuver. Like I said, typically we're talking about an alloy. An alloy is when you have a mixture of metals, An example of an alloy is brass. Brass is made when you melt copper and you melt zinc and you mix them together in the liquid state, and then you cool it down to the point where it solidifies, and then you have a solid piece of brass. But in that brass, there would be zinc, there would be copper, and it would be a solution, all right? I don't have any of those values memorized. There's all kinds of different alloys. If you have some jewelry that's sterling silver, it's a mixture of silver and some other elements that I really haven't studied, but I don't know what the percentages are. If you have, 14 karat gold, it's not pure gold. It's got other metals that are in the alloy, right? Steel itself is not all iron. It's made up of iron with some other elements, zinc and magnesium and some carbon in it in order to make it stronger. So let's just make up an example of, let's say, 0.25% carbon in steel, all right? Just as an example, like a very small percentage. To be honest, I have no idea what it is. Actually, when I made the note, I was going to look up some alloy percentages, and obviously I forgot. So I'm making that up. So what would that mean? That would mean that there would be 0.25 grams of carbon per 100 grams of steel, the overall solution, the overall substance. And when we start doing questions, we'll make that equal to the thing that we're interested in, that we want to find the information about. And again, just to, state it like I did the others, because it is W/W, it is grams over grams. All right? So percentage concentrations are pretty straightforward. We have a knowledge of what a percentage means, and so percentage concentrations are typically used for consumer products because there's not a lot of general people out there that know what a mole is. So to talk about concentration in moles to people who haven't taken chemistry wouldn't work, wouldn't make sense. Tomorrow, we will learn about molar concentration, more useful to us as chemists. But we still see this a lot, so it's important. So let's do some examples here. $140 milliliters of pure acetic acid in 500 milliliter bottle solution to determine the concentration, and it's a percentage concentration. Now, I haven't decided what's the best way to do this one. This one, we're actually looking for the percentage, so you could just treat it like a regular percentage calculation. We've got 140 milliliters of acetic acid. That's the stuff we're dissolving. It's in 500 milliliters of solution. What's the percentage? So I'm going to break this into two parts. If we were treating this just like a regular percentage, we know that percent, and you could put percentage concentration if you'd like, is equal to the, in this case, I've got milliliters and milliliters, the volume of the solute divided by the solution, 140 milliliters in 500 milliliters of solution. In order to turn that into a percentage times 100, and we would have a concentration, okay? Now, the other way I showed you was with the ratios. You could also do it like this. If we're looking for the percentage concentration, that goes up on the top. So I could say X over 100 is equal to 140 milliliters of the solute over 500 milliliters of the solution. And there you can see I've represented it as the ratio. This is the same as this. Either way, it doesn't matter, okay? If I'm solving for this, I'm going to multiply both sides by 100 in order to get rid of this 100, all right? So I'm going to have times 100, and on this side, I'm also going to do a times 100. That cancels that out, and you can see it's the same calculation. When you're finding the percentage, it doesn't matter which form you use, okay? What is the percentage? Did anybody get a value for that? Yeah, what do you got, Leah? 28? 28%? This is 28%. And V/V. Now, if you didn't put the V/V on a test, I would be okay with it. But that's what it is because we've got milliliters per milliliter. Okay? So to find the percentage is pretty straightforward. Now, this is where my lesson is different than the lesson that I have currently online. In the past, we would have turned that percentage into a conversion factor, and you would have used it as a conversion factor. And from talking to students, that's a confusing step. So I'm thinking, let's simplify it and treat it just as a ratio. You can imagine as if we have two solutions here. We've got one that defines the percentage out of 100, and then we've got this other solution that has 45 milliliters of the solute, and I want to figure out what volume of the solution I would have. So again, just generate a ratio. 3% V/V. That tells me that I have 3 milliliters, the V, per 100 milliliters of this solution. So there's 3 milliliters of, it doesn't even say what the solute is, solute, per 100 milliliters of solution. Now I'm going to finish generating the other ratio. It contains 45 milliliters of the solute. Where's my 45 going to go? Where does the solute number go? Yep, in the top. Solute over solution. I have 45 milliliters of the solute, and I'm looking for the amount of solution. Now, in this room, I guarantee that we have some people that are very mathematically inclined, and they're flying through that equation right now. Those of us who are less mathematically inclined, when we have the X on the bottom, we notoriously get the wrong answer because we have to actually bring the X to the top in order to get the right answer. If, when you're solving for an equation that is a ratio like this, and X is on the bottom, just flip it over. Flip the whole thing over, and then the math becomes easier. We can flip the whole thing because we're not changing the ratio by turning it upside down. If you flip it, you're going to have 100 over 3 is equal to X over 45. All right? Now, those of you who are good and strong at math, you don't have to do this. You just cut through the math like you know how to do it. Now, by flipping it, notice what we've done. We've put the X into this position, and it means we can now take the 45 and bring it to the other side. Now, I wrote down last time how to bring it to the other side. I said, okay, we've got to multiply by 45 in order to cancel that out. And what I do to one side, I've got to do to the other side. I multiply by 45. Now, some of you who had various teachers might have learned something called opposite operations. Have you heard of that before? When you go across the equal sign and you're solving for an equation, what was a calculation on one side becomes the opposite calculation on the other side. This was divide by 45. When I bring it over to here, notice it becomes multiply by 45. So you don't need to write that out in such a long way. You could just bring this, pick it up, put it over there, And you can write it now as 45 times 100 divided by 3 equals x. Now, I went through some detail on how to calculate that this time. Next calculation, less detail. We've got to be able to translate that over to the next one. Anyway, what is x? How much of solution would we have? Yep. 1,500? 1,500 milliliters. We got supporters on that. We like 1,500. So here's the ratio again. Look at it. If 3 out of 100 is our percentage, and this has to be the same ratio, then the bottom number has to be big, you know, by the same amount, and 1,500 is what fulfills that. 1,500 gives us the amount of solution that we would need. Okay? So again, it's just ratios. It's as if this is our standard solution, and we've got to make the ratio the same to figure out how much of the solution was needed. So again, in this one, it's asking to determine the percentage concentration. It just says percentage concentration. So I'm looking for that percent number. I said the first time there was a couple of ways to do it. Now I'm just going to go back to one way, and I don't care which way you use. But to keep things all the same, I'm going to use that ratio situation. If I'm looking for the percentage concentration, it means I'm looking for x over 100. I want to figure out what that percentage out of 100 is. X over 100, solute over solution, 7.5 grams over 250 milliliters. And if I'm doing opposite operations, my divide by 100 becomes multiply by 100. What do you got? Three? Two significant digits probably on here, the 250. 100 is a perfect whole number. It's defining the percentage. So let's go with 3.0%. What letters should I put behind this one? What letters should go behind this to represent the type of percentage it is? What letters would I put there? Yep. W/V. It represents weight over volume. Weight over volume. W/V. Per. It's like a divided by, right? It's per volume. Excellent. Okay. I don't know whether you've spotted the trend, but we've done 2 volume per volume questions. We're now on our second weight per volume questions, and we'll do a couple of weight/weight questions. And to keep significant digits, maybe I should have here 8.0. 8.0. It's 2 significant digits. It's weighed to exactly 8.0. The trickiest thing in these questions is to figure out what goes on the top and what goes on the bottom. You need to think, what is the solute, what's being dissolved, and what is the solution, what's the overall bulk solution that we're dealing with in the end. Again, I'm thinking this method is a little better than what I used to do, because as soon as you see 8%, what should you be writing down? What are you writing down first as soon as you see the 8%? I'm hoping this is the part that's a little easier. What am I writing down as soon as I see 8%? Is the classic Monday morning pause. Ryan, what am I writing down when I see 8%? 8 over 100. 8, oops, terrible, 8 over 100, actually 8.0. We actually can put units with that too, but we'll worry about that later. It's actually 8 grams per 100 milliliters, but we'll worry about the units in a moment. Equals. Now we've got to figure out what's the thing we're looking for and what's the thing we're given. Are we given the solute or are we given the solution, and are we looking for the other one? 9 grams of sugar. What is that? Where does it go? Yep. On top, because it's the stuff that's in the solution. And notice it says what volume of juice. The juice is the bulk solution. That's what the sugar is dissolved in. So 9 grams and X. In this case, it'll be milliliters because we're doing weight per volume. Again, flip, opposite operation, get an answer. Going to bring the 9 up to that side. So how much juice could this person ingest? You have an answer there, Sierra? What's that? Well, you'll never know unless we give it a shot. What do you got? 112.5? 112.5 milliliters. We would round that back to 2 significant digits. Now, 2 significant digits, you'd keep the 100 and the 10, and we would go to the nearest 10. 2 significant digits would technically be 110 milliliters, or 1.1 times 10 to the 2 milliliters, but that's all right. We don't like the answer? No. You don't like the way I've analyzed that in significant digits? If I have 2 significant digits, it means that what's that? It would be 8% to 1 decimal place. You see what I mean? Yeah. And that's what significant digits are all about. If I had 8.000%, then I would know I would have exactly 112.5 grams. But if I only know it to be 8.0 approximately, then I only know it to those 2 decimals. That's why I added 1. If I had only 1 significant digit and the juice container said 8, just 8%, you actually have a big question mark. You got to say, well, what is it? Is it 8.4 that rounds back to 8, or is it 7.5? You've got a big range of what it could be, which means they'd only be able to drink about 100 milliliters, right? Because there's so much unknown if you don't know what the decimals are. All right, let's keep rolling. Should be 5. Yeah, again, in my editing. That was yesterday. Whoa, it's not very oriented over in this corner. Whoa, that's a terrible 5. What is going on? It looks like I'm only oriented in the middle. I didn't get that first X very well up there when I oriented the board. If when you orient it, you don't touch right on that dot on that X, then the computer thinks that the image has got a funny skewed shape and is putting my pen mark in a different spot. Again, notice it says determine the percent concentration of the ring. This time it's mass of pure silver in the overall sterling silver ring. What percentage silver is in the sterling silver alloy? And again, if you're calculating a percentage, some of you are looking at that saying, oh, I can do a percentage like that. That divided by that, times 100, beautiful, way you go. That's excellent. Again, just to keep things consistent, I would write, I'm looking for the percentage, x over 100 equals, right, just to keep it consistent as a ratio. And in this case, silver is the solute. It's in the ring. So 11.1 grams over 12.0 grams. If we get really good at that opposite operation, some of you might say, do I have to write that middle step in there? As long as you don't make a mistake, I'm not concerned, because in my mind, I can see me having to go 11.1 divided by 12 times 100, or 11.1 times 100, because it's going to come up here, divided by 12. I don't care. What do we got? Mitch, you got a number? 92.5. This is 92.5% silver, and that's W/W. You don't need the brackets around it. Sometimes you see it with brackets around it. If you have it there, it's great. W/W. 92.5% of that alloy is silver. Again, very repetitive. This is my last one here. It's supposed to be a 6, I think. Now we've got two parts to this question just to keep us on our toes. I've added a little moles calculation in there because that's what we will be doing tomorrow. We'll be getting back into moles. And sometimes if I'm needing some supplies, I've already implied to you that I go to the grocery store and get some baking soda. Very often if we're using hydrogen peroxide or peroxide, we don't order it from the big chemical companies. It's expensive. We just go to the grocery store, get our 3% hydrogen peroxide. And if I'm doing an experiment with it, I may need to know moles. So I have to be able to go from the percentage to the moles. Because as a chemist, I need moles so I can use the mole ratio, so I can find masses. So we will do the first step first, obviously, what mass of sodium fluoride in 1.2 gram sample of toothpaste. So we're doing our ratio that I've taught you, and then we'll do the moles afterwards. So again, as soon as you see the 2.5%, your brain is thinking, I've got 2.5 per 100. This is grams per grams, but we'll leave that out to keep the calculation clean. And again, the question is, what goes where? I'm looking for the sodium fluoride in 1.2 grams of toothpaste. Where does that 1.2 go? Is it the solute or is it the overall solution? Jack, what do you think? So it's on the bottom. We're looking for the sodium fluoride. Excellent. X over 1.2, and we're solving for X. Again, opposite operations. That 1.2 is divided by on this side. It's going to be multiplied on that side. Do you need to write that step? That's how it depends on your comfort value, right? But I would easily just go 2.5 times 1.2 divided by 100 because I see that step.
Sanders, can I please have Ashley Hilton to the office?
Yep. And I'll take a number. Yep. 0.03, and I want another decimal after that. That's it, 0.030. It worked out to be exactly 0.03. Okay, excellent. And that is grams of sodium fluoride. We like that number? It's not very much. It's good. Now for the second part, I want to know how many moles of sodium fluoride is. That is, I have grams and I want to turn it into moles. How do I convert grams to moles? Molar mass. So grams to moles, we know it's the molar mass. We get the molar mass. We do a standard conversion factor that we do, and away we go. We're doing real chemistry again, which is what we're going to be doing tomorrow. So I'm going to need a molar mass of sodium fluoride, NaF1 fluorine I don't use often. 0.0, 19.0. 19.0, 23. Sodium is 23. 23. That should be easy math. 42. 42. 42.0 grams per mole. And we set it up as we always do. 0.030 grams sodium fluoride. I got to get rid of the grams. 42.0 grams per 1 mole. I don't know what's going on. Leah should have had an answer by now. She's slipping. It's all right. Don't apologize. Somebody else want to jump in? Jack, what do you got? You got a number there? Oh, don't have a number because you're waiting for Leah. I understand. Yep. 0.00071 moles. We're like that? Okay. If you put it in a scientific notation, it's a little cleaner. When you get to these really tiny numbers, that's where scientific notation is great. 1, 2, 3, 4, 7.1 times 10 to the minus 4 moles. All right? Okay. So at this point, we've got some practice problems for you to do. Oh, and I wrote on it. Well, that sucks. I can't. My eraser doesn't work. That says, what does that say? That says 284, numbers 2 to 4. Also, by the way, folks, there is a worksheet that is on today's day work page, and the top half of it is percentage calculations. The second half is molar calculations we're going to learn. So also the top half of the worksheet. All right, and you can see it on that on the day's work page. Okay, slightly different way of doing it. I think it is less confusing. By the looks on your faces, you either look non-confused or that's just the Monday morning kind of half asleep face. So I'm not sure whether that was a success or not. We'll find out in a bit. All right, I am going to stop recording and you guys can work away. And I got to access the recorder.